You're watching a YouTube video right now. That video just traveled through equipment owned by your neighbor's ISP, a company in Frankfurt, a data center in Singapore that may or may not be run by the government, and through an undersea cable that Google had wrapped in Kevlar because sharks kept biting it. Yes, sharks. Your video wasn't sent as one piece. It was chopped into thousands of fragments, each one taking a completely different path across the planet. Some went through Moscow, some went through Sao Paulo. A few bounced through routers so old they probably run on prayers and duct tape, but they all arrived in order, unread by anyone in between. "40 years ago, the internet was a highway with no locks, no guards, and no rules. Your data traveled as plain text. Every router between you and your destination could open your packets like postcards, read them, change them, send them somewhere else entirely. Passwords, credit card numbers, love letters to your college crush, all visible to anyone running a checkpoint. And what's a checkpoint? Every router your packet passes through, every ISP's equipment, every internet exchange point where networks meet. 14 to 18 of them on average, each one a potential spy. In 2008, a researcher demonstrated this by sitting in a coffee shop and capturing the login credentials of everyone using the Wi-Fi. It took him about 10 minutes. Nobody noticed. Today, 2 billion people trust this same system with their banking data. The packets still travel through strangers' equipment. They still get examined at every checkpoint. But now they're wrapped in layers of cryptographic armor that would take every computer on Earth running until the sun burns out to crack. The journey starts the moment you hit send. Before your packet can leave your phone, it needs to prove it has the right to exist. Your phone has a secret buried inside it, a 256-bit cryptographic key burned into your SIM card at the factory. Unique as a fingerprint, impossible to extract without destroying the chip. When your phone reaches out to a cell tower, the tower doesn't just accept its word, it challenges it. Prove you are who you say you are. The tower sends a random number. Your SIM card runs it through a cryptographic function called A3A8, using that secret key, and produces a response that only the real owner could generate. If the math checks out, you're in. If not, you're dropped. This happens every time you connect. You've never noticed it, and that's the point. Wi-Fi does something even stranger. Your phone and router need to agree on an encryption key, but they can't just say the key out loud. Anyone listening could steal it. So they use a protocol called WPA3 SAE, built on something called a Dragonfly key exchange. Both sides do mathematical calculations using your own Wi-Fi password, and somehow, and this is the magic, they both arrive at the exact same encryption key without ever transmitting it. It's like two strangers agreeing on a secret word, but only speaking in riddles. Everyone in the room hears the riddles. Nobody else can solve them. Even if an attacker records the entire handshake, they can't brute force the password offline. The math doesn't allow it. Your packet now has its first layer of armor, but it still doesn't know where it's going. You type youtube.com, but computers don't speak English. They need numbers. Your device asks the DNS system, essentially a giant phone book for the internet, hey, where does YouTube live? This used to happen in plain text. Everyone on your network could see what websites you're asking about. Worse, someone could intercept your question and give you a fake answer, redirect you to their version of YouTube, their version of your bank. Now your query travels through an encrypted tunnel called DNS-over-HTTPS. It looks like regular web traffic. Nobody knows what you're asking. When the answer comes back, it's signed cryptographically. Your device traces that signature back through a chain of trust, from the domain to the top-level domain, all the way to the root servers, whose keys are literally kept in safes distributed around the world. If any signature in that chain is wrong, even one, your device returns server failure. Connection refused. It won't tell you why, it just stops. Your packet now knows where to go. Time to hit the highway. There's no single road from your phone to YouTube. There are thousands, and the map changes every second. The internet is divided into about 75,000 autonomous systems. Think of them as independent territories. Your ISP is one. Google is one. The company that runs your coffee shop's Wi-Fi might be another one. Each controls its own piece of internet real estate. But how do they find each other? Every network constantly announces to its neighbors, I can reach these addresses. Those neighbors pass the message on. I can reach those addresses through that guy, and so on, rippling across the entire internet in seconds. This is BGP, the Border Gateway Protocol. It's how your packet knows that to reach YouTube from your apartment in Chicago, it should go through your ISP, then through a regional exchange point, then maybe through a tier 1 network that has direct connections to Google servers. The entire routing table, every possible path to every destination on the internet gets rebuilt constantly. New paths appear, old paths disappear. Your packet rides whatever route looks best at that exact millisecond. The average packet crosses 14 to 18 hops, or separate networks, to reach its destination. 70 to 180 milliseconds, from anywhere to anywhere on Earth. Your grandparents waited longer for a dial tone. But there's a problem with this system, a fundamental flaw that nobody fixed for decades. Anyone can lie about what they can reach. In February 2008, Pakistan's government orders YouTube blocked nationwide. A local telecom announces to the internet, "YouTube lives here now. Send all traffic to me." They meant only to tell Pakistan. They accidentally told the world. Within 2 minutes, YouTube traffic from Tokyo, London, New York, everywhere started flowing to Pakistan into a black hole. The packets arrived and vanished. YouTube disappeared from the internet for 2 hours. In 2014, attackers did this on purpose. They announced they owned Bitcoin addresses, redirected traffic through their servers, and stole $83,000 in a few minutes. A fix was needed to prevent these things from happening again and again. So a framework was developed, RPKI, Resource Public Key Infrastructure. Now, legitimate network owners can cryptographically sign their announcements. I'm authorized to announce these addresses. Here's my proof. Routers can check the signature against 5 global trust anchors and automatically drop anything that doesn't verify. As of late 2025, about 55% of IPv4 space and 60% of IPv6 space is covered. 50-50 odds that your packet's route is actually verified. The internet is half fixed. We'll probably get around to the other half eventually. All this protection used to be slow. The old way, TCP plus TLS, required 3 round trips before you could send a single byte of actual data. Your device says, hello. The server says hello back. They exchange certificates. They agree on encryption keys. They confirm they agree. Then finally, you can talk. Each round trip across the Atlantic takes about 30 milliseconds. 3 of them meant nearly 100 milliseconds of just waiting, shaking hands. QUIC, or quick UDP internet connections, collapse this into 1 round trip. Your device says, hello, here's my key, let's encrypt. And the server says, got it, here's mine, here's your data, done. 30 milliseconds to establish a fully encrypted connection across an ocean. The old handshake alone took that long. But QUIC does something else, something that matters when you're watching YouTube on a train. Your phone has a connection ID, a unique identifier that survives network changes. You switch from Wi-Fi to cellular, same connection. Your train enters a tunnel and your phone jumps between towers, same connection. Your home router gets a new IP address from your ISP at 3 a.m., same connection. You've probably noticed videos don't stutter when you walk out of Wi-Fi range anymore. That's not magic. That's QUIC doing its job while you're not paying attention. Your video was chopped into thousands of packets. Each one took a different path. Some went through equipment running code from the 1980s. Some went through undersea cables that sharks occasionally bite. Some traveled through countries with governments that would love to read them. The pieces arrived out of order, at different times, from different directions, yet your device caught them all, sorted them, verified every signature, decrypted every layer, and assembled them into a perfect picture in milliseconds without you even noticing. This happens billions of times per second for every person on Earth with an internet connection right now. The internet is held together by math that governments can't break, signatures that can't be forged, and the strange fact that even though nobody trusts anybody, not routers, cables, or the networks between you and your destination, the packets still get through. Somehow, it works every single time, at least so far.